Hello, friends. Today, we're going to be introducing logarithms. And so let's just jump right into it. This is topic 2.9, Brian Passwater material. And we were just looking at the last few lessons have been about inverse functions, right? So kind of undoing functions. And so every operation has one way of undoing it, right? So for example, addition, the way that you undo addition, kind of the way that you would solve this equation, x plus 3 equals 7, is by subtraction, right? So subtraction is how you undo that. Multiplication, the way that you do that, the way that you undo multiplication is division. And the way that you undo cubing is by taking a root, right? Cubed root in this case, etc. But what is the inverse function of exponentiation? So in other words, 3 to the x equals 7, what would be the inverse of that? And that's where logarithms come in, okay? And so just as, um, we can write uh, rational numbers in decimal form or in fraction form, so when it comes to exponents, we can write them in exponential form or in logarithmic form. Okay, so that's what we're filling in here if you're following along in the notes, right? Exponential or logarithmic form. Okay, and they can both mean the same thing. So it's a way of rewriting from one form to another form. It would kind of be like writing, x plus 3 equals 7 as x equals 7 minus 3. Means the same thing, although then you simplify. Anyway, uh, so the exponential form, for example, would be b to the a equals c. And that, for example, so 3 to the x equals 7. And then the logarithmic form, log base b of c equals a. So that would be log base 3 of 7 equals x. Okay. So the way that I read logs to myself is I think to myself, the base to the what power gives me the number that's in there, right? So this would be, in my head, I would read 3 to the what power equals 7. I'm kind of going back to the exponential form because that's what I'm most familiar with. So, you know, uh, I could just write b to what power equals c. We're not going to go over how to calculate that yet, but just getting used to the form and what's there. Oftentimes when you see log, like if you look at log on a calculator, most of the time it's log and then that's it. And if you punch it in, log, and then it just gives you parentheses and you can put things in. So log without any base written, right? So the base is b here, also 3 in the example that I used, right? A log without any base written, it's implied that that's log base 10. And then also, you should know this, that ln is natural log. So this is log base e, the natural constant, right? The natural number that we saw in one of the previous lessons. So natural log is used so often it gets its own designation, and log base 10 is just called the common logarithm. Okay. And so, first example, we're going to convert the following equations from exponential to logarithmic form. So this would be log base 3 of 9 equals 2. Right? And again, what that means is 3 to the second power equals 9. Okay, and so then this one is log base 10. So I don't have to write the 10. So I'm going to leave it out for now, just so we practice seeing it. Log base 10 of y equals x. Okay, log base. So again, the base is what we would normally call the base in an exponential function anyway. So log base r of w equals t. And then natural log, ln is the natural log because that's e, log base e of y equals 3x. All right, so e to the 3x power is what equals y. Okay, it just takes practice doing this over and over again. and getting it's like learning a new language. That's really all it is, because you already have the concepts for it. So now we're going to convert the following equations from logarithmic form to exponential form. So this is 7 squared equals x, right? 3 to the x power equals y. And this is 10 squared equals y, right? Log without any base written. It's implied that's the common logarithm, so log base 10. And this is e to the fourth power equals c. Okay, so now um, sometimes logarithms, they seem difficult, right? But sometimes we can evaluate logarithms without the use of a calculator. If we kind of think of it in terms of the exponential form, we can figure out what it is. So for example, log base 2 of 8, I would think to myself, 2 to the what power equals 8. Oh, well, that's 3, right? X equals 3 in this case. Next one, 5 to the what power equals 25. Oh, that's simple, right? X equals 2. Okay, and we can do all these this way. 2 to the what power is 32. Think through that one. I'm going to cheat and look at the answer here. It's 5, right? 2 to the fifth power is 32. And then log no base, right? So that's implied it's 10. 10 to the x power is 100, right? So that means x is 2. 10 squared is 100. Okay. Log base 16 is 4. Interesting, right? 16 to the what power would give me 4. Well, 4 is the square root. Oh, so x has to equal 1/2. No confusing. 3 to the x power equals 1. Uh-oh. How do we get 1, right? 3 to the what power is 1? Well, any number to the 0 power is 1, right? So log base anything of 1 is 0. So x equals 0. So log, again, implied base 10. So 10 to the what power equals 10. Well, in that case, x equals 1. And then what about this? Ooh, interesting, right? 6 to the what power is 1 over 36. Well, I mean, how would I get 36 would be squaring it, but then 1 over, so that means I need a negative exponent. And so x is -2. So again, you have all the concepts for this. It's just a matter of practicing and seeing the different situations. Okay, and we can use a calculator. I'm going to show you how to use a calculator. For these, when you put it into a calculator, it's usually just by default log base 10. But then when we get to C and D, I'm going to show you a trick for getting the logarithms of different bases, because it can be a little bit of a pain in different calculators. Um, so let's take a look. Log of 9, so I'm going to need a calculator for this. In Desmos, on the iPad at least, I go to degree or function, and I've got log there. So log of 9. So this is, again, it's implied. Log base 10 of 9 is 0.95. And then log of 6,125. So again, I go to function log 6125. So that comes out to 3.787 or 3.79, I'll call it. Okay. So again, like what does this mean? This means that 10 to the 3.79 power equals 6,125. That's what it means, just to keep it all in context. Okay, now I need to see log base 2 of 10. So I can think 2 to the what power is 10. That's not something I can do in my head. The way that we can do this here is we take log of the number that's in there, right? Log base 2 of 10. So I put 10 in there. So log of 10. And now I divide by the base, log of the base. Sorry. So now I divide by log of 2. And as long as the log in the numerator and denominator have the same base, so log base 10 of 10 over log base 10 of 2, that's going to give me log base 2 of 10. And so the answer here is 3.32. So again, the idea here is this, that log base 10 of 10 over log base 10 of 2 is equal to log base 2 of 10. Why that works, we'll get into later, but I'm just showing you for now as you're putting things into calculators. There are other ways of changing the base in calculators, but each calculator is different and it can be a little bit of a pain. This is actually probably just feels more like a shortcut, and it works. So I would recommend doing it this way. If you want to look into your particular calculator and how that works, go for it. Um, so the next one, log base 7 of 135. Okay, so log 135 over log of 7, same as log base 7 of 135. It gives me 2.52. All right, now let's look at the graphs here. One of the common usages of graphs, of logarithms, is the way that they're used in graphs. Okay, there are some functions that at the beginning they change very, very little, and then they change a lot at the end. Particular some exponential functions, right? Like we've seen here. And so here is a graph of the population from the years 1620 to 1820. So year zero is 1620. And then the marked years are every 20 years. They've got data here for every 10 years or so. And you can see that in the beginning, if there are changes, you can't really tell in the graph, right? So instead of doing a regular normal scale, we can use a logarithmic scale. Okay, and if you look then on the right side, this is that same data, but on a logarithmic scale. And you can see the differences in the beginning much better than you can see the differences in the beginning on the normal scale. So sometimes this is how we'll graph things, right? You might see things on a logarithmic scale. One place where logarithms is used is in, for example, sound, using decibels. Decibels uses a logarithmic scale. And there are other applications as well. So let's take a look at this. um, so it says the population of English Americans in the United States. So they want us to plot the next 3 years. So 1840, 1860, and 1880. And we're given these populations. And so we've got to find out, okay, like how do we get these numbers? How do we plot these? Okay, so I take a look at, I've got 17 million. So that's in the 10 to the 7th range, right? So this is going to be in the beginning here. I've got 10 to the 7th, so I'm going to be just above that. And that's going to look like, do this in blue. So 20, 1840. So that's 220 years after, right? And that'll be here, trying to line it up on the side there. Next one is 31,000. So that's going to be up there too, just a little bit more. And then 260 years later, so 1880 is 50,000. And so that's probably halfway to the next one, right? Because 50,000 is halfway between 10 to the 7th and 10 to the 8th. Right. So, wherever, again, I'm pretty far from the axis over here, so I'm just trying to estimate about where I think it would be. Okay. So something like that. Almost like it's almost linear at that point, kind of continuing that. Looks like a line, I should say, the shape of a line. And so here you can see what it looks like with the lines in there. So it's a little easier to graph here. Okay, so it says plot the following points in the same coordinate plane above. Okay, so 1, comma 20. Well, I go over to 1 horizontally, and then I'm looking for 20. Well, this is 10 right here, right? And so 20 is going to be right there. 20, because this is kind of going up by the powers. Once I'm at that new power of 10, then it's going up 20, 30, 40, 50. And then from here, it goes up 200, 300, 400, etc. So this is going to be 1 comma 20. So that's point A. Point B is 2 comma 300, so I'm going over to 2. And then here's 100, 200, 300 is going to be right there. So that's point B. Point C is 3 comma 2. Um, so 3, so I'm starting at 1, and then 2 is right here. Careful, right? Because that bottom line is not 0, it's 1. And so that's C. D is 4 comma 15. And so in order to get to 15, well, that's tricky, right? Because I don't have a particular line for that. 10, the next line up is 20. So I'm going to be about halfway between those two. Right? D is going to be about here. And then 5 comma 350. Well, I've got 100 is here, 200, 300. So 350 is going to be in between, about here. So I didn't label that D, and there's E. Okay. So there's your basic introduction to logarithms, using kind of looking at the graphs, intro to the graphs, and then introduction to the notation of it, and a little bit of how to use the calculator to calculate some things. So thanks for watching. Don't forget to like and subscribe.